Hello friends, in this session we define inverse of a function, its domain, range and graph. We see that not every function has an inverse. We describe that graph of an inverse of a function is the reflection along the line y equal to x of the graph of the given function. We consider a number of examples. We will also consider an important class of inverse functions called inverse trigonometric functions. Inverse of a function. In layman's language, the term inversion gives the idea of a reversal. For example, sucrose, the table sugar, is made up of glucose and fructose. Reversal process gives glucose and fructose from the sucrose. In mathematics, the term inverse is used to describe functions that reverse one another in the sense that each undoes the effect of the other. Now, we are going to discuss this fundamental mathematical concept. The idea of solving an equation y equal to f of x for x as a function of y, say x equal to g of y, is one of the most important ideas in mathematics. For example, using basic algebra, the equation y equal to x plus 3 can be solved for x as a function of y given by x equal to y minus 3. If we take f of x equal to x plus 3 and g of y equal to y minus 3, and if these functions are composed in either order, they cancel out the effect of one another in the sense that g of f of x equal to g of x plus 3 equal to x plus 3 minus 3 equal to x, and f of g of y equal to f of y minus 3 equal to y minus 3 plus 3, that equal to y. Pair of functions with these two properties, they are so important that there is a special terminology for them. If f and g are functions that satisfy the conditions g of f of x equal to x for every x in the domain of f and f of g of y equal to y for every y in the domain of g, then we say that f is an inverse function of g and g is an inverse function of f. We also say that f and g are inverse functions. For example, the functions f of x equal to x raised to 5 plus 3 and g of y equal to fifth root of y minus 3 are inverse of each other, because g of f of x equal to fifth root of x raised to 5 plus 3 minus 3 equal to fifth root of x raised to 5 equal to x for every x in the domain of f. F of g of y equal to f of fifth root of y minus 3 equal to all raised to 5 of fifth root of y minus 3 plus 3 equal to y minus 3 plus 3 equal to y for every y in the domain of g. It can be proved that if a function f has an inverse, then that inverse is unique. Hence, if a function has an inverse, we call that function as the inverse of f, which we denote by the symbol f inverse. Read f inverse. We bring your attention to note that the minus 1 in f inverse is not an exponent. F inverse x does not mean 1 by f of x. In the definition of inverse of a function, we have used two different independent variables x and y for f and f inverse, but there are occasions on which it is desirable to use the same independent variable, say x, for both. Hence, with the notation of the inverse of a function, if f has an inverse, then f inverse of f of x equal to x for every x in the domain of f, and f of f inverse of x equal to x for every x in the domain of f inverse. We call these equations as the cancellation equations for f and f inverse. These equations imply the following relationship between the domains and ranges of f and f inverse. Domain of f inverse equal to range of f and range of f inverse equal to domain of f. Given that the function f has an inverse and that f of minus 3 equal to root 2, then we find f inverse of root 2 as follows. Applying f inverse to both sides of the equation f of minus 3 equal to root 2, we obtain f inverse of f of minus 3 equal to f inverse of root 2. Using one of the cancellation equations, we get minus 3 equal to f inverse of root 2, that is f inverse of root 2 equal to minus 3. In general, with the aid of cancellation equations, we have the following. If a function f has an inverse and f of a equal to b, then a equal to f inverse of b, that is f inverse maps each output of f back into the corresponding input. This illustrated in the following diagram. We now give a method for finding inverse functions. Method: if an equation y equal to f of x can be solved for x as a function of y, say x equal to g of y, then f has an inverse and that inverse is g of y equal to f inverse of y. We prove this as follows. Substituting y equal to f of x into x equal to g of y gives x equal to g of f of x, and by substituting x equal to g of y into y equal to f of x gives y equal to f of g of y. These two equations shows that f has an inverse and that inverse is g of y equal to f inverse of y. Let f from R to R be denoted by f of x equal to 2x minus 3. Find a formula for f inverse. Let y be the image of x under the function f, that is y equal to f of x equal to 2x minus 3. Mark as equation number 1. Consequently, x will be the image of y under the inverse function f inverse. We solve for x in terms of y in equation 1, obtaining x equal to y plus 3 all divided by 2. Then f inverse of y equal to y plus 3 all divided by 2. Replace y by x to obtain f inverse of x equal to x plus 3 by 2, which is the formula for f inverse using the usual independent variable x. Geometrically, the inverse of this straight line y equal to 2x minus 3 is also a straight line y equal to x plus 3 all divided by 2, obtained by interchanging x and y. Proceeding as in the above example, we remark that inverse of a straight line y equal to mx plus c, where m is non-zero real number, is obtained by interchanging x and y and is given by x equal to my plus c, or simply y equal to 1 by m into x minus c. We find a formula for the inverse of g of x equal to 2x minus 3 by 5x minus 7, where the domain of g excludes x equal to 7 by 5. Also, we find natural domain of g inverse. Writing y equal to g of x, we obtain y equal to g of x equal to 2x minus 3 all divided by 5x minus 7. Then we solve for x in terms of y as follows: 5xy minus 7y equal to 2x minus 3, or 5xy minus 2x equal to 7y minus 3, or 5y minus 2 whole into x equal to 7y minus 3. Hence, x equal to 7y minus 3 whole divided by 5y minus 2. Thus, G inverse of y equal to 7y minus 3 whole divided by 5y minus 2. Now, using the usual independent variable x, the formula for G inverse is G inverse of x equal to 7x minus 3 whole divided by 5x minus 2. Here the natural domain of G inverse excludes x equal to 2 by 5. Existence of inverse functions. So far our discussion in this session was the definition and the method of finding inverse of a given function, provides the inverse exists. The method discussed so far may fail due to any of the two reasons. The function f may not have an inverse, or it may have an inverse, but the equation y equal to f of x cannot be solved explicitly for x as a function of y. Thus, it is important to give conditions that ensure the existence of an inverse, even if it cannot be found explicitly. If a function has an inverse, then it must assign distinct outputs to distinct inputs. For example, the function f of x equal to x square cannot have an inverse, because it assigns the same value for to x equal to 2 and x equal to minus 2, namely f of 2 equal to f of minus 2 equal to 4. Thus, if f of x equal to x square were to have an inverse, then f of 2 equal to 4 would imply that f inverse of 4 equal to 2, and the equation f of minus 2 equal to 4 would imply that f inverse of 4 equal to minus 2. But this is impossible, because f inverse of 4 cannot have two different values. Hence, f has no inverse. Another way to see that f of x equal to x square has no inverse is to solve the equation y equal to x square for x as a function of y, which gives the two values x equal to plus or minus square root of y, showing that x is not a function of y. We already know from these session functions that if a function carries different elements in the domain to different images, it has a special name, one-to-one or injective function. Our discussion so far in this shows that if a function is one-to-one, it has an inverse and vice versa. So, a one-to-one function is also called invertible. We state that a function has an inverse if and only if it is one-to-one. With this result, the horizontal line test, which says that if a function f is one-to-one, then each horizontal line intersect the graph of f in at most one point, can be written in the following form. A function f has an inverse if and only if its graph is cut at most once by any horizontal line. The function f of x equal to x square has no inverse, as the figure shows a horizontal line that cuts the graph of y equal to x square more than once. So, f of x equal to x square is not invertible. Figure shows that the graph of y equal to x cube is cut at most once by any horizontal line. So, f of x equal to x cube is invertible. its inverse can be obtained as follows. Y equal to x cube implies x equal to y to the power 1 by 3. Hence, the inverse function is given by f inverse of x equal to x raised to 1 by 3. The curve in the figure is not a function with a set of real numbers as domain, but a function say f with the domain in the interval closed interval minus to 16. The function f has an inverse since its graph is cut at most once by any horizontal line. To evaluate f inverse of 1, we view f inverse of 1 as that number x for which f of x equal to 1. From the graph we see that f of 2 equal to 1, so f inverse of 1 equal to 2. Let f be a function defined on an interval I, and let x1 and x2 be any 2 points in I. 1. F increases or increasing on I if x1 less than x2 implies f of x1 less than f of x2. 2. F decreases or decreasing on I if x1 less than x2 implies f of x2 less than f of x1. A function that is increasing or decreasing on I is called monotonic on I. The graph of an increasing function is always rising as it is transverse from left to right. The graph of a decreasing function is always falling as it is traversed from left to right. These figures gives us the intuition geometrically that graph of increasing or decreasing functions are cut at most once by any horizontal line. Hence, increasing and decreasing functions are one to one, and hence they are invertible. A method for finding inverse from the graph of f. We now focus on describing the way of getting graph of an inverse function f inverse from the graph of f and vice versa. There is a nice relationship between the graph of f and f inverse. For this purpose, we treat x as the independent variable for both the functions. So, we can compare the graph of y equal to f of x and y equal to f inverse of x. If ordered pair AB is a point on the graph of y equal to f of x, then b equal to f of a, or equivalently a equal to f inverse of b. This means that ordered pair BA is a point on the graph of y equal to f inverse of x. This shows that reversing the coordinates of a point on the graph of f produces a point on the graph of f inverse. Similarly, reversing the coordinates of a point on the graph of f inverse produces a point on the graph of f. The geometrical effect of reversing the coordinates of a point is to reflect that point about the line y equal to x. Hence, the graph of y equal to f of x and y equal to f inverse of x are reflections of one another about the line y equal to x. We summarize theorem. If f has an inverse, then the graph of y equal to f of x and y equal to f inverse of x are reflections of one another about the line y equal to x. That is, each graph is the mirror image of the other with respect to the line y equal to x. As an example, graph of the function y equal to 3x and its inverse y equal to 1 by 3x are shown in the figure. They are reflections of one another about the line y equal to x. It can be seen that ordered pair 3 1 is a point on the graph of y equal to 3x, while ordered pair 1 3, the point obtained by reversing the coordinates of ordered pair 3 1 is a point on the graph of y equal to 1 by 3x. As another example, the graph of the function y equal to x cube and its inverse y equal to x to the power 1 by 3 are shown in the figure. They are the reflections of one another about the line y equal to x. We have noted earlier that the inverse of the function g of x equal to 2x minus 3 all divided by 5x minus 7 with x not equal to 7 by 5 is g inverse of x equal to 7x minus 3 all divided by 5x minus 2 with x not equal to 2 by 5. Graphs of these functions are displayed in the figure. Restricting domains for invertibility. In an example above, we have seen that f of x equal to x square is not invertible as its graph fails the horizontal line test. We are now going to show that two invertible functions can be made out of f of x equal to x square if we partition the domain into two intervals, so that the piece of the function defined on each interval in the partition is invertible. We restrict the domain of the function to the set D of non-negative real numbers, then g of x equal to x square with x greater than or equal to 0 is invertible as its graph passed the horizontal line test. Its inverse is the square root function given by g inverse of x equal to root x with x greater than or equal to 0. If we restrict the domain of the function to the set S of negative real numbers, then h of x equal to x square with x less than 0 is invertible as its graph passed the horizontal line test. Its inverse is obtained as follows: y equal to x square with x less than 0 implies minus x equal to y to the power 1 by 2 with y greater than 0 implies x equal to minus of y to the power 1 by 2 with y greater than 0. Hence, the inverse function is given by h inverse of x equal to minus of square root of x with x greater than 0. The functions g of x and h of x are called restrictions of the function f of x equal to x square with x belongs to R, because each is obtained from f of x merely by placing a restriction on its domain. In particular, we say that g of x is the restriction of f of x to the interval closed to 0 open infinity, and that h of x is the restriction of f of x to the interval open minus infinity closed to 0. Geometrically, the graph of g of x equal to x square with x greater than or equal to 0 and g inverse of x equal to square root of x are reflections of one another about the line y equal to x, as are the graph of h of x equal to x square with x less than or equal to 0 and h inverse of x equal to minus of square root of x. Now, inverse trigonometric functions. A function f of x is periodic if there is a positive number p such that f of x plus p equal to f of x for all x. The smallest such value of p is the period of f. We assume that the learner of this course is familiar with the trigonometric functions. While defining the trigonometric functions, throughout our discussion, we take that all angles are measured in radians unless degrees or other unit is stated explicitly. We note that in astronomy, angles are measured in degrees, but in calculus, radian measure is preferred. In the figure, we have plotted the unit circle centered at the origin. It can be seen that when an angle of measure x and an angle of measure x plus 2 pi are in standard position, their terminal rays coincide at the same point on the unit circle. The two angles therefore have the same trigonometric values, that is cos of x plus 2 pi equal to cos x and sin of x plus 2 pi equal to sin x. The period of cosine function is 2 pi, since 2 pi is the smallest positive value such that cos of x plus 2 pi equal to cos x for all x. Similarly, period of sine function is 2 pi. 6 basic trigonometric functions, their domain, range and period are given below. Graph of the trigonometric functions are given below. These 6 basic trigonometric functions do not have inverses because their graphs repeat periodically and hence there are horizontal lines which intersect the graph more than once. So, in order to discuss the inverse of trigonometric functions, we restrict their domains to the intervals on which they are invertible. The inverse sine function. If we restrict the sine function sin x to the interval closed interval minus pi by 2, then it is invertible, and we define that y equal to sin inverse of x is the number in closed minus pi by 2, closed pi by 2 for which sin y equal to x, that is y equal to sin inverse of x with minus 1 less than or equal to x less than or equal to 1. The inverse sine function is also called arc sine function and is denoted by arc sin x with a minus 1 less than x less than or equal to 1. The graph is obtained by reflection across the line y equal to x of the curve sin x with a minus pi by 2 less than or equal to x less than or equal to pi by 2. Evaluating an inverse sine function is the same as asking what angle, say y, be put into the sine function to get x. The restrictions on y given above are there to make sure that we get a consistent answer out of the inverse sine function. We know that there are infinite number of angles that give the same sine value. Restricting to the interval closed interval minus pi by 2 for taking the angle y gives the value of the sine function exactly once. Also, we note that the graph of y equal to sin inverse of x with a minus 1 less than or equal to x less than or equal to 1 is a portion of the curve x equal to sin y. Similarly, y equal to cos inverse of x or y equal to arc cos x is the number in closed 0 closed pi for which cos y equal to x. We list the domain, range and inverse of the trigonometric functions in the following table. Conclusion. The basic concepts like domain, range and graph of an inverse function are discussed in detail. Above concepts are explained using basic trigonometric functions. Students are advised to find the domain and range of various inverse functions. Hope this session was beneficial to you. See you next time. Goodbye.